Let's do a really quick problem here. And this is from the Hibbeler book, Mechanics of Materials. And what it says is this: the shear stress strain diagram for an alloy is shown in the figure right here. You've got a bolt, you can see it here. That bolt has a diameter of 0.25 inches. It's made of that material and is used in the lap joint. Determine the modulus of elasticity, which is capital E, and the force P, so that force is what's being applied here, that's required to cause the material to yield. Take the Poisson's ratio to be 0.3. All right. So let's see how we would go about doing this. So we want to find E, okay, modulus of elasticity, and we need to find the force P, right? And we have nu, which is 0.3. That's Poisson's ratio. So we've got all of these things going on, and then we've got this information here. Okay, well, if you remember, in chapter 3 of this textbook, we have this relationship with capital G, so modulus of rigidity, or shear modulus of elasticity. We know that has to equal capital E over 2 times 1 plus Poisson's ratio, which is nu. So I've got this information. Now I'm looking for capital E. I know nu, right? I know this. So if I can find G, I can get what I'm looking for. Right? Now how could we get G? Well, what about this right here? So we can use this diagram here to find G. And G, the shear modulus of elasticity, is just going to be basically the slope of this elastic portion of this line. All right? So slope would be rise over run. Okay, so rise would be the 50. And then the run, the horizontal, would be 0.004. And that gives us 12,500. Okay, and the units there would be KSI because this is KSI here. All right. So now we've got G, so we can plug that in here. And then we're going to set it equal to E over 2 times 1 plus 0.3. And then solve for E. We get 32,500 KSI. All right, not too bad, right? So the key here is to know that you can use this diagram, this elastic portion of this curve, to find G. A lot of people forget you can do that, but that is how that is defined. Okay. Next, we want to find the force P. All right, so we can see the force P is here. So let's kind of draw a diagram of that bolt, right? So we've got this, we've got the force P being applied here, and then that's going to cause a shear, right? So we're going to have a Vy there. Okay, I'm not sure why I called it Vy, but that's what I called it. Y I assumes to mean yield. Okay, so let's go ahead and find that force. Okay, so shear stress at the yield point is given as 50. Okay, so we have that value. And I know that shear stress has to be a shear force over the area. Okay, so we got this Vy, so that's our yield force here that we're going to have over area. And let's go ahead and plug this in. So we've got the 50, that's KSI. It's going to equal that shear force. Now looking at this diagram, what would the shear force be? Well, it's got to be P, right? Because we want equilibrium. So we're going to put P here. And then the area, how do we find the area? Well, diameter was given, so we can use that. So our area would be pi over 4 times 0.25 inches squared. And again, we're using pi over 4 because this is diameter, right? This is not radius. Okay, so this leaves us with one equation, one unknown. We can solve for P. We get 2.454 kip. And there you have it. So just a very short example, just reminding you of this equation and how we can use the shear stress strain diagram to find G, okay? And then, you know, how those are related. All right. See you guys next time for another one.